Yeah, hi. We are just waiting for the result of the awards for the students, and then quickly we announce them and begin again the session. Sorry for the delay. Okay, seems it in 5 minutes, so we should begin again. Sorry, really.
Hello, hello, it's working. So hello everybody, and first of all, we are very sorry for the delay, but we were choosing the best poster and the best oral presentation, and you know there were a lot of good posters and good presentations, so the deliberation was quite long of students, okay? So I will announce, so it's going to be quick. So for us, after a lot of deliberation, the best student oral presentation was done by Ryo Kinoshita from the University of Tokyo. Okay, I don't know if he's still present. Okay, Ryo is not here. He couldn't wait. We are sorry. Okay. So we passed to the best student poster presentation. So we have chosen Cecilia Andreazzi from Fundação Oswaldo Cruz and Universidade de São Paulo. The title of her poster was Using Ecological Multiplex Networks to Model Infection Spreading in Multi-Host Systems. So if you can come here.
So we are approaching the closing sessions of the workshop, and I guess we could not be in better hands than the hands of Bernard Cazelles from Ecole Supérieure, Ecole Normale Supérieure, and Michael Turedi from UC Davis. I had prepared a very long introduction, trust me, okay? So for both of you, since you deserve that. But given that we are given a delay, I guess I am skipping that and inviting Bernard for his talk. Thank you.
Thanks, Claudio. It's okay. So first, I have to thank the organizer for inviting me in this very nice conference and beautiful cities. So I will speak about statistical and mathematical approaches for a better understanding of dengue epidemics. So I can summarize my talk just by 3 words, simply: necessarity, nonlinearity, and stochasticity. So just that. So I will speak mainly about dengue, but as I see a lot of nice presentation of dengue virus yesterday and this morning, so I skip all my slide on dengue. So I will go directly to the different model approaches. So this is an overview of my talk. First, to focus on statistical approaches, so about wavelet, and then to focus on the mathematical model with time-varying parameters and also about model selections. So I start with wavelet. So wavelet, with wavelet, we can estimate the spectral characteristics of the time series as function of time. We can have the possibility to quantify the different spectral characteristics of a time series, but also we have the possibility to have information of the evolution, the time evolution of the space evolutions of these spectral characteristics. So wavelet analysis decompose time series simultaneously in the time domain and the frequency domains. And since 2001, with the paper of Brian Grenfell and co-worker, there is more and more paper that use wavelet in ecology and epidemiology. Something like between 40 and 50 paper in 2014 and 2015. So what is wavelet? Wavelet is simply simple mathematical functions with 2 examples here with some specific characteristics. For example, the Mexican hat, but I will use just the Normale wavelet, which is simply the sinusoidal functions multiplied by Gaussians. We had 2 parameters to these functions: a translation parameter to have the possibility of moving the mother wavelet along an axis. It can be a time axis or even a space axis. And we have also another parameter named the scale of the wavelet to have some large wavelet and to very thin wavelets. So with this kind of wavelet, we simply compute the wavelet transform. This is simply the convolution product between the time series X and the complex conjugate of the wavelets. So to try to be simple, this wavelet transform can be viewed some sort of matching between a time series with a time series and a signal and a wavelet with the scale parameter at the position B. So when the matching is good, we have a high value of the wavelet transform. When the matching is bad, we have a low values. So we have a high or low value here, and we move for different value of B and a different value of the scales to obtain a wavelet power spectrum. What is important to stress with continuous wavelet, more or less a continuous wavelet. With continuous wavelet, what is important to stress is that there is a mathematical relationship between the scale of the wavelet and the periodicity and the frequency of the wavelet. This is not the case with discrete wavelets. So with wavelet decomposition, we can compute different things. So the wavelet transform, or also the reverse of wavelet transform. We can have, when we have a complex wavelet, like in Normale, we have the real part and the imaginary part. The norm, so we compute the wavelet power spectrum, which is simply the square of the norm of the wavelet transform. We can, when we have two time series, we can compute the cross wavelet power spectrums. And we can also compute wavelet coherency, something like some sort of correlation, cross variance divided by the variance, cross spectrum divided by the spectrum of the two time series. So to try to summarize what we have come like as result in the following. So I just show you an example. We have a time series, an SIR model with period 2. Small epidemic, large epidemics. When we put a wavelet of period 2, the matching is good. We have high value of the wavelet transform, high value of the wavelet power spectrums. And in my graphs, this high value will be coded in red. So we have a red point. So then we move the wavelet of period 2 along the time axis, and we have this red band. We do the similar thing with a wavelet, for example, of period 4. The matching is bad. We have low value of the wavelet transform, low value of the wavelet power spectrums. So we have, and this low value is coded in blue. So we have, and moving this wavelet along the time axis, we have blue values. So we do the same things for different scale, different periodicities, and we have this kind of graph. In this kind of graph, say you that in this time series, we have many two periodic components, one about 2 years, and one smaller, about 1 year. This line is the cone of influence. It means that when we compute the wavelet power spectrum at the border, the time series is enough length, long, so we need to add 0. So all the value outside of the cone of influence have been computed with 0. So generally, we don't like to interpret result outside the cone of influence, but when we have this kind of signals, what's the effect of adding 0? Adding 0 just decrease the value of the wavelet power spectrum. Just one short example, not about dengue, but about cholera, to show you why it's important to use wavelet with this kind of time series. So when you study the link between global climate and epidemiology, one of the key papers is the paper from Mercedes, the group of Mercedes, the paper by Javier Rodo in Science, this one, not sure. So they tried to find some relationship between El Nino and cholera in Bangladesh. So I do exactly the same thing. They use Fourier spectrum. So I do exactly the same things, but with data of cholera in Ghana. So the continuous line is the cholera cases between 1975 and 2003. And the dashed line is the source oscillation index, the proxy of El Nino. So I smooth the two time series using Fourier using singular spectrum analysis, and then I compute the Fourier spectrum of the two time series. So we have the Fourier spectrum of the cholera time series, and dashed line the Fourier spectrum of the source oscillation index. So what we remark that we have very similar power spectrums. So we can say that the two time series have the similar oscillations. So there is few chance that cholera influence El Nino, so there is perhaps some causality. So but if you analyze this two time series with wavelet, the results are less conclusive. So the two time series, the two smooth time series, the wavelet power spectrum of cholera in Ghana, the wavelet power spectrum of source oscillation index. What is inside the dot dash line is a significant region obtained by bootstrapping techniques. So what we remark when we compare the two power spectrums is that we have a 2-3 years component that is marked here between 87 and 95 here, but this at this time there is no significant component in the source oscillation index time series. For the 3-4 years, 4-5 years component here is more or less present during all the time series in source oscillation index, but disappear in the case of cholera in Ghana between 85 and 95. So when we compute the coherency, some sort of correlation between the two time series, there is very few areas that are significant. There is just one small here, oops. Small here and small here. So clearly, these two time series have similar oscillating component, but not at the same times. So we cannot conclude that the source oscillation index and Nino influence cholera in Ghana. There is some teleconnection, but not in this case. So now I shift to dengue. So my story with dengue began with this paper published in Nature in 2004 by the group of Dunberg. They say that there is some wave, 2-3 years waves that start in Bangkok and propagate around all the Thailands. And they find no links with climate. So I get the time series. At this time, we have 72 provinces of Thailand. And in first time, I focus on the incidence in Bangkok and in the average incidence in the rest of Thailand. So I tried to find a relationship between this time series and El Nino, and we use a multi-ENSO index, another proxy of El Nino. So in the dark, we have the El Nino time series. In blue, we have the average Thailand time series, and in red, we have the Bangkok time series. When we apply the wavelet coherency, we find large significant area for the 2-3 years bands, and the drift from this 2-3 years band to a 4-5 years band here for the Thailand and for Bangkok. So when we have large El Nino here and here, we have large epidemics of dengue in Thailand. So we can compute the oscillations component for the 2-3 years band here. We have quasi perfect synchrony between dengue and El Nino, and we have a drive, and after we have a perfect synchrony for the 4-5 years band here. We can do the same things. Well, we do this with El Nino, but we can do the same things with rainfalls. And we also find a nice correlation between dengue epidemics and rainfall when we have large El Nino events here and here. So we can do the same with rainfall and El Nino. Now it's clear that El Nino influences the local climate, and the local climate influences dengue. So I will skip this one and go to the second point on with wavelet. So the idea is to analyze 72 time series of dengue in Thailand. So for this, I use a method proposed by Tristan Rouillet in a paper about tuna. He have, during his PhD, he have something like 200 time series about tuna in different parts of the world. So he proposed this method. So we have two wavelet power spectrum map. So it's a pairwise comparison. So we have two wavelet power spectrum map. We compute the covariance. Then with the singular value decomposition, we have access to the leading pattern and the singular vector. And with leading pattern and singular vector, we compute the distance between the two maps, some sort of dissimilarity distance. And based on this dissimilarity distance, you make some classical clusterings. So with the 72 time series, we have this group. So time series of this group, this province, for example, have similar wavelength power spectrum and then similar dynamical characteristics. So if I choose 4 different clusters, this one, the small one, and the other one. And if I put the different cluster on a geographic map of Thailand, we obtain this well-defined arrangement of with large area with similar dynamical properties. So, for example, in A, we have a cluster for the east part of Thailand with a marked seasonal mode and a 2-3 years mode around before 1990s. In the north, the seasonal mode is marked also, but this part have been reduced. In the south, the seasonal mode is very thin. And the variance of the time series is mainly in the 2-3 years mode after 90. And in the central part and in Bangkok, the seasonal mode disappear. And we have just variance in the 2-3 years modes. So the next step, this is an ongoing work that had been stopped in 2010, something like that. So perhaps it will be reappear in the following months. So the next step will be to try to understand why we have this kind of dynamical patterns in Thailand. So I applied the same methods to rainfalls and to average temperature, and we find some very similar map with 4 clusters. So the idea, perhaps we have some idea to try to answer to these questions, is how we can quantify the relationship between these different spatial patterns. We have the dengue spatial pattern and similar pattern for rainfall and temperature. It will be great to try to explain this pattern by the 2 other one, or 2 other one, or also kind of variable like altitude or socioeconomical factors. So I will stop for the statistical part and shift to mathematical models. So my first focus will be on a two-strain dengue model with time-varying parameters. So for all the modeling part, I will use this kind of approach. We use oops, I have some trouble. I use state space models and Bayesian inference based on Kalman MCMC or particle filter MCMC, except the first result that use some strange maximum likelihood iterated filter. So the great advantage of using this kind of state space models is that we have 2 sets of equations. The first set of equations describes the propagation of the disease, some sort of SIR model, for example. And the second set of equations describes the observation process. So generally, we observe just new cases, and we use some probability models for this observation, Poisson process, negative binomial process, or Gaussian process. So this kind of method has been put in some tools, in some plug-and-play tools. That has been done by 2 of my previous students, Sébastien Ballesteros and Joseph Duro. Initially, the tool was named Plum when Sébastien was in the Brian Grenfell group in Princeton. So he moved, and now since 2-3 years, the tool is named SSM for state space model. So if you want to get the tools, we can use Google and put SSM, GitHub, and Ballesteros to obtain the tools. So we use 2-strain models, the model for Mayra Aguiar. So we have populations that are susceptible. They can be infected by strain 1 or strain 2, removed from strain 1 or strain 2. We have a period of transcendental immunity of, in average duration, 1 divided by alpha. And after this period of transcendental immunity, you can be infected by strain 2. when we have already get strain 1, we can be infected by strain 2, and if you have get strain 2, we can be infected by strain 1. So the transmission rate in this first part is classical sinusoidal functions. And what is interesting here, we have the phi parameters. If it's greater than 1, the secondary transmission is enhanced. We have antibody-dependent enhancement. And if phi is less than 1, we have some sort of cross protections, so it's more difficult to get secondary infections. So we have applied, Sebastian have applied this kind of approach to dengue on the data set from Thailand. So I just show you an example of Chiang Mai. So in gray, we have the notified credible interval. I'm not sure I can say credible interval for MIF. So it's confidence, it's frequencies. So the notified confidence interval for MIF. In red we have the data, and black, in dash black, we have the average or the median. I don't remember. So what it's all line, but I put on the I don't remove the title. So it's clear that in these cases we have chaotic attractors. So we have chaotic dynamics in the data and in the models, and we have some specific type of chaotic dynamics named UPCA for uniform phase and chaotic dynamics. We have an epidemic each year. So if you compute the power spectrum of the time series, we have something around between 10 and 40 months. Each year we have an epidemics, but the dynamic is chaotic and the amplitude is completely chaotic. So it's very difficult to fit this kind of chaotic dynamics due to the sensibility to initial conditions. So we have the fit, we have the maximum likelihood profile for different parameters. For example, R0 is around 2.5. And what is interesting with this kind of data is we have phi, and phi it's in average around 1. So we can be conclude about if there is some cross protection or antibody-dependent enhancement. So the second step is to forget the fluctuation of beta, the sinusoidal fluctuation of beta, and you make the hypothesis that beta, the transmission rate, follow a Brownian process. Log of beta follow a random Brownian process, and sigma is the volatility of this random process. So we will try to reconstruct the dynamics of beta, the time evolution of beta, just using Bayesian inference. So I show you some results from Cambodia in the province of Phnom Penh. So we have the time evolutions of beta. In this case, we have used PMCMCs, so it's notified credible intervals. So what is clear is that we don't have sinusoidal beta evolutions. In general, we have a fast growth of beta and a slow decay. We have also annual variations due to environmental condition, to climatic condition, to different population of mosquito, but also due to the property of the strain. For example, in 2007, a new strain appeared, and the property of this strain, DEN4, if I remember, is different than the previous one. So after, the idea is to try to explain these variations of this time evolution of beta. So I use climatic variables. So I use wavelet also. So in the first graph, we have beta in blue, in black, we have humidity, and we have a large significant coherence for different periodic components and for the annual periodic components, and perfect synchrony between the evolution of beta and the humidities. We have the same with maximal temperature in blacks, but in this case, we have a delay between 4 months. So we have a peak on temperature, and 3-4 months after, we have the peak in the transmission rates. And after, we have the peak on dengue. We have similar thing with the global index. This is the IOE for Indian Ocean Index. The relationship is better than with El Nino. So the next step will be to incorporate this climatic variable in the model to explain the fluctuation of beta. So this is already been done with, for example, with the malaria model with Laneri. This is also already done with Lewiston about flu in Israel, for example. But here we have clear information of the fluctuation of beta. We don't put the assumption that there is a link between the fluctuation of beta and the climate. But the idea will be also to introduce some socio-economical factors. For example, in Cambodia, we have the percentage of urbanizations by districts, the percentage of household with electricity by district, the density of market also. So we can try to explain the fluctuation of the transmission rate by some different socio-economical factors. So my last point about model selections. So in this case, we have data from rural area from Cambodia. So the idea is always the same. The objective always the same, a better understanding of the biological and environmental mechanisms underlying the recurrence of dengue epidemics. So in Cambodia, that's in many parts of Asia, as in Brazil also. We have an epidemic each year. So when we make model we need to be able to reproduce the next epidemics, even if at least qualitatively. So for this, we use dynamical models, stochastic model root in data. We use Bayesian inference with MCMC and particle filters. And we, as Aaron said 2 days ago, we have the possibility to compute the likelihoods. And as we compute the likelihood, you have the possibility to compare different models, but also to compare the hypotheses that you have put in the models. So the applications in the real area of comprehension. So the data came from the European project DEN3. They have investigated rural village in the radius of 30 kilometers around the capital of the province, Comprehension. You see there are 3 main hospitals, and there is also some health centers. So during 2 years, 2012 and 2013, they obtain information about index cases. They go to the hospitals or to the health center. They ask questions to people that have fever and dengue. So this is the health, the index cases. And after they go to the household of the index cases to test all people living in the households of the index cases, and also on the household around the household of the index cases to have information of the different cases linked to these index cases. So for all individuals, we have the seropositivity. We have symptoms. People have symptoms or not symptoms. And also if you have symptoms about D7, D10, also D15, if I remember correctly. We have also the characteristics of the virus, then 1, then 2, then 3, then 4. And I hope that in the following weeks, we'll have also the sequences of all these viruses. So we have the different information on the different virus. So in 2012, each time DEN1 dominates. In 2012, we have DEN1 and DEN4, and we have the 4 virus in 2013. So we have index cases and index in the community. So we have in 2012, 260 cases and 673 in 2030. So we have the time evolutions, the time series of cases in this part of Cambodia. So, but we have also symptomatic cases and true asymptomatic cases. What is very surprising here is that we have less than 5%, just 5% of asymptomatic cases. If you know the literature, people say there are between 14 and 80% of asymptomatic cases. I think that due to the sampling design here, we have some bias in the observation of asymptomatic because all the index cases are severe cases. They are at the hospital, so it's severe cases. And we think that in households with severe cases, there are few probability of observing asymptomatic cases. So after I try to fit different model on this data, so a classical SIR model, SERI model, and also a model with a vector. It seems that dengue is transmitted by vector, so it's, but we have very few information about the mosquito. So even it's large investigations, they obtain something like 8,000 mosquito, 15 are Aedes, 15% are just Aedes, and less than 1% are positive to dengue. And 2 male mosquitoes are positive to dengue also. So I use a particular model by the group, also another time by the group of Mercedes Pascual, with a model about malaria. So in this case, as we don't have a lot of information about mosquito, L can be viewed as a product between infected mosquito and a transmission rate between mosquito and humans. K can be viewed as latent, can be some sort of variable proportional to latent infected mosquitoes. And the transmission between, for transmission between human and mosquito, we have a new parameter beta prime. It is the product between the transmission between human and mosquito and the population of susceptible mosquitoes. So we put whole and no variable in just one parameters. So then we use a stochastic version of this model. We use the state space framework with observations that follow Poisson process, observations are weekly new cases. And we just focus on the children population. We have 48,000 children aged less than 15. So we use PMCMC, so we have the posterior distribution for the different parameters, but we have also this kind of output of the models. So we have for SIR model, the infected populations, we have the incidence, and we have also the fluctuation of susceptible and the fluctuations of removed peoples. And we have the incidence and our observations. So the difference between the two is because we have two different reporting rates. We have an estimation of the reporting rate for 2012, around 5%, and a reporting rate around 10% for 2030. So we have also used asymptomatic infections. We simply say that people that have been infected have symptoms in high or don't have symptoms, they are high A. And the same for the vector, the model with the vector. And we simply also make the assumptions that the 5% of asymptomatic observed in the dataset is not true. So you try to fit this proportion here. And we have also a specific reporting rate for asymptomatics. So we have 5 models, 5 fit of the models. All fit seems quite good, but it's difficult to say that this model is better than this one. So it's classical to compute different statistical indices. So we have the number of observations, the number of parameters, the log likelihood. We put just as an indication the log likelihood per observations because we don't have the same number of observations. So it's difficult to compare archaic information criterions because we don't have exactly the same number of observations. So if you just focus on statistics based on likelihood, it seems that the better model is the sample model, this one, SIR model. you have the better Ecole information criterions. But we have also, as we have different number of observations, we have also make simulations of the model and compute the mean square error based on the observations of the models between the difference between observations and the simulation based on the posterior distributions. So we have this kind of simulations. We don't see observation. There is some observation, but we see no things. So it seems that this model seems better based on Ecole information criterion, but we have a large variance on the predictions of the models. This is not the case for the two of the model and the model with vector. This is the same things when we introduce asymptomatic infections. We have a larger variance for the samples models. But clearly, the main drawback of the simplest model is the too large depletions of susceptibles, with not enough recruitment to get initial levels of the population of susceptible. So we don't have enough susceptible to generate an epidemic next year. But we know that there will be, in 2040, there is an epidemic, and 2030, 50 also. So as we have 48 children less than 16, so if you make the assumption of homogeneous recruitment by birth, we have just be able to recruit to have just 3,000 newborns each year, so it's not enough to replenish the susceptible compartments. So perhaps it's more clear that if you compute the effective R, so with the sample models, we are the average of effective R never cross 1. So we will not be able to generate an epidemic in 2040 and 2050. But with the model with vector, with asymptomatic or with no asymptomatic, effective R cross 1, so we'll be able to generate an epidemics. So the main difficulty with this kind of approach is that we have some problem of identifiabilities for some parameter, for some initial conditions. So in this case, I put the correlation between the different parameters that have been estimated by the particle filter, MCMC, and we see here that is very large negative correlation between the initial proportion of susceptibles and the beta 0 of the transmitter that permits the computation of the transmission rate. So we have two kinds of models. Some model with low initial susceptible variable, low initial susceptible population of susceptibles, and high value of beta. This is model with vector. And we have also a model like SIR model. We have very low, a low initial population of susceptible, but high initial population of susceptibles, and no value of beta. So to conclude about this part, it's clear that for model selections, one has to take into account not only the statistical index like IKK, DIC, and so on, but we have also to take into account the epidemiological coherence of the model trajectories. So I think there were too few papers that publish fit of models, and very rare paper publish also the dynamic of susceptible, for example. We have just information of number of infected. So many problems remain, especially those related to the parameter identifiability. So perhaps in area, there is a low automation, so automaticians can give some information about identifiability. So it's clear that more data are needed. I think seroprevalence is important because we can have an independent estimations of the initial population of susceptibles. But with virus sequences, we can also make use phylodynamic approaches. So we can, for example, couple coalescence models and propagations models to have a better definitions or a better estimation of the transmission rate. So I will stop here, just some global conclusions. So in public health, there is more and more need of predictive tools, but it's clear that these predictive tools need to be adapted to the complexity of the propagation of the disease for parameter inference, for testing hypotheses, and for model selections. And it's clear that one of the current weakness of all this approach is the lack of adapted data set. So for me, as modeler, I think that the limiting part of the epidemiologic modeling exercise is the availability of data. So I have to thank all the members of the Dengue consortiums, the member of Pasteur Cambodia, Clara Champagne that started PhD on model selections, David that work on the phylodynamics, and Kevin that make a lot of R graph. Thank you.
So, merci, Bernard. And we are now in the hands of Michael. But Michael has to switch the computers. Okay, so I don't know how long this is going to take. So I can share with you some of the thoughts that I had to introduce Michael that I didn't do. Okay, so since I am in a business school, it makes some sense to mention an economist. And in this case, is a winner of the Nobel Prize, Paul Krugman. And I like a lot Krugman's column in the New York Times, and he offers very interesting insights in economical issues and so on. But this is not the reason why I am mentioning him. The reason I am mentioning him, and this is going to be related to what Michael is going to present, is that a few months ago, he listed all his predictions for the past 10 years, indicating in which one he was right and which one he was wrong. Okay, so, and I found this very interesting because we should all be doing this, okay? So we have our models and we should be telling people and also keeping a track of the models that went right and those that did not. And I think that Krugman is setting a very interesting example that we should follow. And what this has to do with Michael is that the last time I attended his talk, he was revisiting his model on Wolbachia, a model that he is very famous for. And he was rethinking some of the structure of the model and identifying the limitations of using the model that was developed for Drosophila in the context of mosquitoes. Okay, so I guess that his computer is ready, and so let's go.
So I apologize for at least one person who's heard a lot of this talk before. But I think many of you, maybe the vast majority of you, have never heard me speak before. Some of you heard me speak about this topic 10 years ago when I first visited Brazil to visit INPA to give talk. George heard a version of it 10 years ago. So it's fun. I mean, I've been a professor at Davis for 39 years. My background is in mathematics, but I always wanted to do biology. So after I got tenure at Davis, I asked this friend of mine, Jerry Coyne, if he could please teach me how to do experimental work. And Coyne taught me how to do Drosophila work. And 30 years ago, Ari Hoffman and I discovered something quite interesting about Wolbachia. And then, like 10 years after that, people started thinking about Wolbachia after Hoffman and I had shown that Wolbachia can spread very quickly in nature. People like Scott O'Neill started thinking very hard, can we use this Wolbachia to actually do something practical? Okay. I mean, a lot of people come up with a lot of ideas. And then 10 years after that, Scott got the first $8 million from Bill and Melinda Gates. And last couple of years, he's got another $50 million from the Gates Foundation and the Wellcome Trust to actually implement this idea in the field. So a pretty amazing story for, you know, a math kid who sort of learned to do some simple biology to, you know, just be lucky and make a discovery. And I will repeat the story, how for 25 years, I deeply misunderstood mathematically what I had seen biologically in nature, but that mathematical misunderstanding of nature is precisely the correct mathematical framework for these manipulations that we're doing in nature. Okay, that's my talk. Are there any questions? Right. So this talk is a collaboration with my great friend Nick Barton, with whom I've worked for about 30 years now. The star of the show are these little red dots. So these little red dots are in an early embryo. Those are the Wolbachia. These are the nuclei of an early Drosophila embryo. And this is Drosophila that I work on, Drosophila simulans. And this is the mosquito Aedes aegypti into which we have put the Wolbachia, and from which we hope to stop spreading dengue and chikungunya and maybe even Zika, but we'll see. So the story is, I'm going to tell you this story. I'm going to go through it quick. I have way too much to say, but I'm going to tell you quickly the old story from 1991, how Ari Hoffman and I watched Wolbachia spread in nature. I'll tell you about my mathematical understanding, or my mathematical hypothesis about why it spread, and my understanding involved bistability of the system. That story, okay, that story involved this bacterium, maternally inherited bacterium, spreading in natural populations at 100 kilometers per year, 100 kilometers per year, radically transforming all of the Drosophila in California and in most of the US in just a decade. Just amazing. That's what inspired people. Wow, what an incredible tool. The argument was that these bacteria were intrinsically slightly deleterious, but they could spread anyway, okay? And that inspired people like O'Neill to think about how can we exploit these? Yeah, okay, so this is the truth-telling part. So I'm a lucky person. That's just the way it is. Some people are lucky, I'm lucky. So we discovered this Wolbachia spread in California 25 years ago. 10 years ago, we saw it happen again. Actually, 5 years ago, we saw 2 different Wolbachia spread rapidly through Australia. Seeing a replicate made it clear that we had to be wrong for reasons I'll explain. I think natural Wolbachia systems are not bistable, but are monostable. They want to increase intrinsically from very low frequencies. On the other hand, when we take Wolbachia from flies and put them into mosquitoes, we can demonstrate clearly that that system is bistable. And I'll tell you about experimental work, and I'll tell you about field observations that I think unquestionably demonstrate bistability. Then I'll tell you where we are with respect to our dengue project. And I say over the years, I made a lot of mathematical predictions. Some are right, some are wrong. But here's the punchline at some level. We watched Wolbachia spread in Drosophila simulans at 100 kilometers per year. Right now, we are watching Wolbachia spread in Aedes aegypti at about 150 meters per year. And that makes perfect sense in terms of bistability. And I'll show you how it fits in with simple reaction diffusion predictions and modifications of those diffusion predictions to deal with long-tail dispersal. But they didn't make any sense in terms of the original systems that we studied. Okay, so that is my talk. And here, I'm going to give it again now. So here's my first postdoc. This is Ari Hoffman. Ari came to work with me because of the stuff that Coyne and I were doing, and he and I discovered together Wolbachia in California populations of Drosophila simulans. When Ari went back to Australia, the first thing he did was to look for the Wolbachia. So this species, Drosophila, who knows Drosophila simulans? Drosophila simulans is sister to Drosophila melanogaster. These flies come out of Africa. They're invasive species that are now everywhere on the globe where humans are. Okay, so simulans is everywhere. Simulans is Australia. Ari went back to Australia, looked for Wolbachia. No. But he found Wolbachia in the sister species Drosophila melanogaster. And later, when molecular tools were available, he found a new Wolbachia called WAU in Drosophila simulans. Those will all figure into the story. Scott O'Neill. So what is Scott's story? Scott was introduced to Wolbachia by my postdoc, Ari Hoffman, when he was a graduate student. Then he became a postdoc in the US. And Scott, who can be kind of an asshole, is also an extraordinarily generous scientist because as a postdoc, he developed the first PCR tools. So how do you know if an insect you have in nature has Wolbachia or not? Okay. In the bad old days, we had to establish reference lines and do these crosses. It was like a ridiculous amount of work. Now you just take a fly, a butterfly, anything, and just do PCR. That was developed by Scott O'Neill as a postdoc, and he gave us the primer. Sorry, he gave us, right, the talk is almost over. He gave us the primers. He gave us the primers before he'd even published them. Pretty cool. And he established that Wolbachia were horizontally transmitted. And here's why that big grin, $60 million. I mean, come on, not bad, huh? And here he is on O'Neill Street. O'Neill Street in the town of Gordonvale, which is where we first released Wolbachia. Okay? Yeah, I can't resist. Gordonvale, famous, and so we consider our scheme biocontrol, the first attempt at biocontrol of a human disease. Any other attempts at biocontrol? I know. How about the cane toad being released in Australia? Where was it released? In Gordonvale, exactly where we first released Wolbachia. Okay. And here's my pal who I like to embarrass by calling him the world's smartest man, Nick Barton, who independently developed all the mathematics for the bistable reaction diffusion as a graduate student working on a natural hybrid zone. So I'll tell you what Nick and I have been doing. And so here I am in June with Raphael, when he was much more handsome, Raphael, just a few months ago. I don't know what's happened to him. And so these are the two leaders of the Eliminate Dengue project here in Brazil. So we're trying to implement this strategy of controlling the spread of dengue in Rio right now. So Wolbachia, you've heard this many times, maternally transmitted, extremely common, and on the order of half of all insects. Horizontally transmitted on an evolutionary timescale, but mainly maternally transmitted. Wolbachia became famous. So there's a nice story. How did we find out about Wolbachia? How were they discovered? They were discovered by somebody looking through a microscope and saying, what's wrong with these mosquitoes? These look like bacteria that are living in these mosquito cells, and that's what they were. So this man first discovered Wolbachia as bacteria in a mosquito cell. They weren't discovered to do anything interesting in nature. Their effect was discovered in the 1950s by a man named Lavin studying Culex pipiens, and they were named Wolbachia pipientis. Ralph Barr, a colleague at Los Angeles, discovered only in the 1970s that this phenomenon that Lavin had studied was caused by these Wolbachia. And so they became famous for this phenomenon called cytoplasmic incompatibility, which you've heard about many times, but they do other things to make infected females produce more progeny than uninfected females. They kill males, induce parthenogenesis, and feminize genetic males. They can enhance fecundity, reduce fecundity. Ultimate story, because they are maternally transmitted, they evolve towards mutualism. So if you make the simplest mathematical model of what the evolutionary trajectories should be of Wolbachia. Because they're maternally transmitted, the big evolutionary push is to help those females produce more progeny. The most interesting discovery in the last 10 years was that among the ways they do that was to suppress various other microbes in their host. In particular, they suppress viruses. This was discovered by a Portuguese postdoc, Luis Teixeira, working in Mike Ashburner's lab in Cambridge initially. Okay, and this is what we're using in an attempt to control dengue now. So cytoplasmic incompatibility, you've seen it all before. Uninfected, infected individuals. Infected females can mate with an infected male or uninfected and produce infected progeny. If an uninfected female mates with an infected male, there's often a reduction in progeny. In mosquitoes, all of the embryos die. In my species, half of them die. In Drosophila melanogaster, about 5% of them die. Very interesting interaction among Wolbachia and genotypes of their host, among species, and you can show variation within individual species as well. But the big story is they want to evolve to be mutualistic. Okay, so they were discovered in the 1950s and first modeled by these people, Kaspari and Watson. Watson was in the math department at Princeton and must have been really embarrassed to do such trivial mathematics. What they knew at the time only was cytoplasmic incompatibility. I'm convinced, sadly these people are long dead, I'm convinced that Watson was embarrassed to publish such a trivial model, and he said, can't we make this a little bit more interesting? Suppose that the infection lowered female fecundity. Totally made up story. No data whatsoever in 1959. In fact, no data until Hoffman and Torelli published it in 1988 that Wolbachia might reduce fecundity. Okay, made up story. But if you make up that story, cytoplasmic incompatibility fecundity cost, you get an interesting dynamic where it's a bistable system, where there's an unstable point, so there's a frequency-dependent advantage associated with cytoplasmic incompatibility. We postulate a frequency-independent disadvantage. So if you start above this point, you go to fixation. Below it, you go to loss. Okay? So just made up. If half the embryos die, there's a 5% cost. And these are from our field populations in California. Those are the estimates. You predict an unstable point about 0.1. The point is, or a point is, that once the infection gets established, it sweeps through. So in Drosophila, my Drosophila in California, on the order of 10 to 15 generations per year. So in 2 years, a population is completely transformed. Mosquitoes, Aedes aegypti, have on the order of 10 generations per year also in most places. You can generalize that model. Who cares? So I'm going to present this cartoon model. You can build, and I'm going to emphasize this idea that there's an unstable point. It's crap, right? I mean, the real dynamic is a high-dimensional system. You have to deal with age structure, effects at all these different ages. It's a cartoon to think that you could think of this as a unidimensional system with an unstable point. But it's a useful fiction, as I'll show you. What did we discover in California? Well, Ari did these transects, collected flies all over the state, and found only the flies in Southern California had this infection. All of the flies in the Central Valley in Northern California were uninfected. When we first studied it, we found new things out about the biology. We found that this infection in flies was imperfectly maternally transmitted. We showed that about half of the embryos in nature died from incompatible crosses. And we showed in the laboratory that the infected females were systematically less fecund than infected females, on the order of 10 to 20%. Only once in nature did we see that. We've estimated this parameter in nature in about 10 different experiments where we directly compare the number of eggs laid by wild-caught females who are infected versus uninfected. Only once did we see a 5% cost. Most of the time we couldn't document anything, but we could see it repeatedly in nature, in the laboratory. The point is, when we generalize this model and look at the dynamics and ask, how should the frequency change if it's rare? When it's rare, there are two things going on that argued for bistability. One is imperfect maternal transmission. We still see that today. On the order of 5% of the embryos of Drosophila produced by infected females are uninfected. That is not true in mosquitoes. In mosquitoes, it's 100% maternal transmission. But in Drosophila, that was on the order of 0.95. And we thought in the lab that was on the order of 0.9. So for two reasons, we postulated bistability. You still have the unstable point, slightly different formula. So what happens with bistability in nature? There's a beautiful integral criterion, but roughly speaking, if you have two forms that form alternative stable state, there's an unstable point between them. The variant whose unstable equilibrium, crudely speaking, is below 0.5 is the one that tends to spread spatially. So this is what Nick Barton was studying in nature. He was studying grasshoppers that had two different chromosome configurations. Each configuration was perfectly fine by itself, but if you formed an individual as a hybrid between these forms, those heterozygotes routinely produced defective gametes. And what Nick predicted was that the more fit form, the more fit homozygote would spread in nature. And so that's why I call this a Bartonian wave. What Ari and I saw was this infection that was previously restricted to Southern California very rapidly spread through California. Okay? So that after a few years, all populations in California are about 93% infected, which is what you predict from our simple model with imperfect maternal transmission and cytoplasmic incompatibility. Okay? So that's what inspired. So what's the story? You have this bacterium that you think induces significant fitness costs, yet will spread rapidly in nature because of this reproductive manipulation. So what inspired people like Emil is they wanted to modify insects. So for instance, you might want to make mosquitoes, you might want to make Anopheline mosquitoes unable to transmit malaria. We know that we can find in nature the genetic variants so that they won't transmit malaria. Well, okay, let's take those variants and get them to spread. Why won't they spread? Answer, they're at low frequency in nature because they are intrinsically deleterious. Those refractory genes are selected against by natural selection. This seems to be, the Wolbachia seems to be an engine capable of pushing something through a population despite inducing a fitness cost. So it's precisely this story, which I think is now bullshit, about having documented this extraordinarily rapid spread of a Bartonian wave of Wolbachia in nature that inspired the efforts to use it for disease control. So again, I'm going to tell you why I think that's bullshit in nature, but it's exactly the right way to think about our introduced Wolbachia. Okay? So here's the story. As I say, I'm a lucky guy. So I visit Australia every year. I was visiting Hoffman, and he always introduces me to his students. He has this new student, Peter Kreisner, who wasn't sure. This is, you know, like his first week in graduate school. Here's this old guy visiting from California. Why don't you talk to Torelli? So I said, Peter, Ari had told me a little bit about follow-up work that had been done in Australia. I said, Peter, you have to work on Wolbachia. There are all these open questions. It's a slam dunk that you'll get a good dissertation. Just study Wolbachia. We'll talk together. We'll Skype. We'll suggest some project. We'll come up with good things to do. So Peter, this is Peter's dissertation work. I'm going to tell you about the spread of two different Wolbachia in the same species of Drosophila that we saw in California. These are two different variants of Wolbachia. This one, WRI, is mine, the one we discovered in Riverside. This is the one that Ari discovered himself when he went back to Australia. What's different about them? This one kills half the embryos. It does the famous story of reproductive manipulation. This other one, WAU, does no reproductive manipulation. No reproductive manipulation at all. You mate infected males with uninfected females, everything's fine. They produce the same number of progeny. We can't see a fecundity count. It's also imperfectly maternally transmitted. If you look at this one, on the order of 97% of the eggs of an infected female are infected, about 3% are uninfected. Okay? Why is it maintained? Well, we're not quite sure, but we think it's probably mutualism. So here's the story. I won't go through the details, but Ari discovered this Wolbachia in the early 1990s, and when he discovered it, it was rare everywhere in Australia. Okay? A friend of ours moved back to Australia from the United States 5 years later, and Bill Ballard, surveyed these populations up and down the coast. He found that this infection that doesn't cause cytoplasmic incompatibility had increased in frequency. Then one of Ari's postdocs, Andrew Weeks, surveyed in 2004. These frequencies had stayed the same. The infection was now prevalent in Tasmania, but also a new infection had come in. My infection from California. It come in not just in one place, Cairns, where we're doing the mosquito experiments, Melbourne, where Ari has his lab, and Tasmania, where nobody works on these flies. Nobody works on these flies up in Cairns. Once my Wolbachia gets in, my Wolbachia causes cytoplasmic incompatibility against both uninfected individuals and females infected with this other Wolbachia. It starts spreading like crazy. It spreads over the top of the blue infection. Now, Eastern Australia looks exactly like California. Okay? What story are we going to tell now? Well, we can't tell a bistable story. This one's not bistable. There's not. What pushes it in? Our best guess, we don't understand the mechanism, is it does something to help the flies. And it reaches an equilibrium between its fitness advantage, an advantage that we still don't understand, and imperfect maternal transmission. So it's like mutation selection balance. Natural selection wants it to go up, but imperfect transmission drives it down and it reaches an equilibrium. My Wolbachia comes in 3 places. You know, you can be lucky once, right? We saw this thing come into California. Now we see it's come in 3 places in Australia and sweep from all of them, starting from very low frequencies. That's an inherently, I argue, that strongly suggests monostability of all these Wolbachia, natural Wolbachia versus bistability. Okay, and here are the mathematical conditions that have to be satisfied, and we're doing experiments now to test the hypotheses about what the fitness advantages have to be. Okay, we can show that if you establish cages that have loads of viruses in them, these Wolbachia definitely sweep these populations rapidly through cage populations that we can establish in the lab. Okay, so back to dengue. So claim. Natural Wolbachia infections are most likely Fisherian, unstable 0.0. Torelli and Hoffman were wrong about this famous story, but yet I'm going to tell you about applying bistability to understand the spread of Aedes Wolbachia and Aedes aegypti. And again, point of reference, both in Australia and in California, the spread of Wolbachia 100 kilometers per year. 100 kilometers per year. Okay, and we'll see in Aegypti, it's between 100 and 200 meters per year. What the hell's going on? Why is it so different? So this is a cool story. I won't go through this story. When we watched Wolbachia spread in California, we also saw a mitochondrial variant spread. So we identified a mitochondria. So mitochondria are maternally transmitted, as are Wolbachia. We saw a mitochondrial variant in Southern California that swept through, okay? This is a prediction about how it, so it's the fact that it would be associated with the infection, that all the infected people would have the infected mitochondria, that's a trivial prediction. A non-trivial prediction is how that infected Wolbachia goes into the uninfected individuals that have infected maternal ancestors but don't get the Wolbachia. Anyway, here's a prediction I made in '92 that worked. So you've heard all about dengue, emerging disease, increasingly prevalent. Brazil is now, so you've heard about insecticides. Brazil is now spending on the order of $1 billion a year on insecticides to control dengue. There's no vaccine, no cure. So Scott's a lucky guy too, because he got $6 million to try an idea that completely failed. So I'm going to tell you about what I hope will be the success of our project, Truth in Advertising. The project that was originally proposed was a complete failure. What was the original project? The original project was to shorten the long, I'm not going to go through the details of the biology, but females only transmit Wolbachia when they're old for a mosquito, 2 or 3 weeks old. Scott's idea initially was to put in a Wolbachia that halved the life of those mosquitoes. If he could have the lives of mosquitoes, they would not live long enough to transmit. That's what he sold to the Gates Foundation for the original what, 6 or 8 million. So this is the data from Drosophila showing that it halved the life. Here is the data from Aedes aegypti showing that it halved the life. Okay, so it'll halve the life, but will it spread? Okay, so this is why I did this theoretical work a few years ago, trying to figure out what the unstable point should be if you had various effects of the Wolbachia. Suppose it shortened life, decreased daily viability, changed fecundity, and changed development time. And the answer crudely is that you could predict the unstable point as a fecundity cost, a viability cost divided by the CI advantage. With complete cytoplasmic incompatibility, that's 1. Okay? You want that unstable point to be below a half. Okay? You're already having the viability. So you don't want to also decrease fecundity. When they look, you can do the math a bunch of different ways. When they looked at the fecundity of the females infected with this life-shortening Wolbachia, they have the fecundity also. So the unstable point is going to be on the order of 0.7. And something that has an unstable point of 0.7 will never spread spatially. You can release all you want. So we were literally in the last year of the 5 years of the Gates funding, and I called a meeting in Cannes that I called the death of popcorn meeting, because you could show mathematically there was no point in doing releases because the project would fail. These things could never spread. And then a miracle happened. Louis Teixeira, this postdoc, he's studying the ability of natural Drosophila to withstand natural viruses. And he had some Drosophila that withstood the viruses, some Drosophila that did not withstand the viruses. Being a geneticist, he did reciprocal crosses to try to understand the underlying genes. He found out that it wasn't genes, it was Wolbachia. O'Neill instantly jumps on this and says, the heck with life shortening. Let's see if this will block, if this non-life shortening block, Wolbachia, will actually block the transmission of dengue. So Luciano Moretta, the other Via Cruz person, was visiting Scott's lab. He did the experiments, produced this wonderful paper in Cell showing that Wolbachia not only blocked dengue, but also chikungunya, and I believe he has new data suggesting that it also blocks Zika. Okay. Now, these variants are not all created equally. So we've investigated systematically only 2 Wolbachia. Let me repeat. Half of all insects have Wolbachia. Half of all insects. There are many millions of insect species. There are certainly tens of thousands of significantly different Wolbachia out there. How many have we looked at? Count them, 2. Okay, those two have interestingly different properties. One is absolutely, these are both come from Drosophila melanogaster and were put into Aedes aegypti by O'Neill's lab. If you put in the life-shortening one, it really completely blocks dengue proliferation. Completely blocks, but it'll never spread. So that's nice. It'll block, but you'll never be able to use it. This other one blocks well, but not completely. So there's a recent analysis by Neil Ferguson showing that this incomplete level of blocking should be sufficient to severely reduce, if not eliminate, the spread of dengue in nature. We'll see. Okay. I'm going to tell you about the field releases we did and how reaction diffusion equations can be used to understand their dynamics. So the first releases we did, 2011, Yorkeys Knob and Gordonvale, isolated populations. We chose this not because we were sick fucks, wanted to do it the same place the cane toad was, because we were using this as a big population cage. Aegypti only lives with people. This is pure sugarcane, no Aegypti here. So we were using this isolated community as a big population cage. One here, both completely isolated. Now, how many mosquitoes? So people worry about how many mosquitoes do you have to release. This shows how many mosquitoes we did weekly. So, and I was there and did this. I could not resist. I went there to help do the releases. This is how many mosquitoes we would release once a week in each of these tiny communities. Cumulatively, we roughly released a number of mosquitoes on the order of a half to equal the number of mosquitoes in nature. So we were sort of doubling the population every week. You did that for 10 weeks. Dramatic overkill, but rapidly transform these populations. You can raise, no matter how small your office is, you can raise that many mosquitoes in your office, sufficient to transform an area in nature about 1 square kilometer. That's a significant number. That turned out to be a natural unit in terms of a natural spatial unit. So we don't want to ultimately just protect isolated community. We want to protect Rio. We want to convert Ho Chi Minh City. Do you have to do the whole city at once? No. The natural unit, and I'll explain this, the natural unit is on the order of 1 square kilometer, and you don't need a vast number of mosquitoes to do that. Okay? And they'll stay there, and they will slowly spread. Right. So here's what actually happened in our first field trial. As they say, this is shock and awe. You know, this is the carpet bombing of Dresden. We released a ridiculous number of mosquitoes and completely converted these populations in 3 months. And they have stayed converted for 3 years. So if you go to those field populations now, the frequency of Wolbachia is over 98%. You take those mosquitoes that have been in nature for 3 years and reproducing in nature, you ask, after being in nature, do they still block the dissemination of dengue? And the answer is yes, they block at least as well as they did when they were in the lab. Okay, so it seems to be a stable strategy. But again, we don't want to isolate. We don't want to do tiny populations. We want to do cities. So, you know, I'm proud to be embarrassed that I had the bistability story wrong. So I'm very defensive. Do I have the bistability story right now? So I claim I was wrong about Wolbachia and Drosophila, but now I claim that Wolbachia in Aedes aegypti is definitely bistable, but I was equally confident before. Why should you believe me this time? Okay? I'll give you 3 reasons. 4 reasons. I'll give you a lot of reasons. I didn't know I had so many reasons. I'll give you four reasons. They briefly escaped when we were first released them, and the brief escapes went nowhere. I did a mathematical analysis of the rate at which they were introduced, and to understand the rate at which they were introduced, given the number we were putting in, you had to postulate a fitness cost on the order of 20 to 30%. I'll show you an example where this Wolbachia can't cross a road. Can't cross a road. And I'll explain what I mean by that. In these recent experiments that Ari did, going back to these tiny villages that we transformed, you can collect in nature the infected females, literally go across the road and get the mosquitoes that aren't infected and compare their fecundity. The Wolbachia infected females are 20% less fecund. So a very significant fecundity cost, and they live slightly less long as well. So let me this is my favorite of these stories. So first of all, when Wolbachia when we released it here, a few of them escaped to these nearby villages. We were freaked out. We reported this in our Nature paper in 2011, but then those infections quickly went away. They did not establish from very low frequencies. What's much more interesting is what's going on here. So there's a beautiful coastal highway that runs up and down Australia. It's called the Bruce Highway here. So this is a city of about 1,000 people. Here's a new development across the road of about 600 people. Mosquitoes are constantly flying across the highway or getting blown across the highway. What happens? What happens? So here's where we released. This place has stayed transformed for 4 years now. The mosquitoes keep crossing the road, but the frequency has never become appreciable here. The highest frequency we've ever seen across the road is about 15%. We monitored for 4 years. The average frequency is about 11%. That's based on 2,700 observations. You can do simple mathematics of a migration selection balance to predict that the unstable point is at least 0.21. Okay? So definitely bistable. And I think the unstable point, and I'll show you a little more about this, is probably on the order of 0.25 to 0.3. And you'll see what the implications of that are. So why bother? Because I had it wrong the last time. That's why I bother. So what are the properties? At what rate do we expect these introduced Wolbachia to spread? How wide should the waves be? What does it take to initiate these waves? And what does it take to stop them? So the bad news is, so the width of the waves is a very pretty mathematical result that says if you watch one of these waves spread, the width of the wave tells you something about the dispersal distance, which is a critical parameter you need to predict wave speed. The rate at which the waves spread depends on how much migration there is and the position of the unstable point. What does it take to initiate a wave? Well, you have to transform a larger and larger area as the unstable point goes towards a half. What does it take to stop a wave? And the answer is less and less as the unstable point approaches a half. So what I'm going to tell you about are the original predictions that Nick and I made based on a reaction diffusion model with a cubic dynamic that approximates Wolbachia dynamics. Then I'm going to tell you about robustness calculations we've done recently where we did discrete time, discrete state approximations to look at the consequences of long-tail dispersal. Okay, why bother to do all this? Because, as I say, we want to transform cities. We don't want to release everywhere. We thought that we could just seed a city in a couple places and it spread like wildfire. That is not true, sadly. But we've done experiments now where we release in a continuous landscape in a confined area. O'Neill did this in 3 areas. So this is about 1 square kilometer. This is about a half a square kilometer. This is about 1/10 of a square kilometer. Okay? And again, released way too many mosquitoes. Within a couple months, had completely transformed these populations. So these are our release areas. So total release, we released in total over 10 weeks about 10 times as many mosquitoes as were there initially. So shock and awe, releasing way too many mosquitoes, way more than are necessary, but we know this works. And again, way more than necessary, but not a difficult task. It's not hard to release 110,000 mosquitoes. When we release in those little cups, each cup would have about 100 mosquitoes in it. You go into your yard, release these. People complain a little bit, but they want to get rid of dengue and don't complain too much. So Parramatta Park, about a half a square kilometer. In this tiny area called Westcourt, Scott was just wanting to make fun of me. Torelli predicted you couldn't successfully release he doesn't believe any of this math crap. We'll just go ahead and do the experiment. So Scott's approach to all this, even though I'm sort of the resident theoretician, is, fuck the mathematics. I'm going to do the experiment and let's see how it goes. And then Torelli can follow behind and see if the math agrees with what we actually observe. So the answer is we release so that within a few months we transformed the release areas. But do these things spread in nature? Okay. Now, many of you have presented Wolbachia models, and all of you have presented more biologically realistic models than I have ever used for Wolbachia. All of your models have had ecology. All of them have tried to deal with density dependence. Nick and I have tried to blow past all that. The problem is, it's real nice to make a more realistic model. And as a biologist, you would think we would be motivated to make the most realistic model we can. But all those models have loads of parameters that in general we do not know how to estimate. And we know we're going to have to estimate those parameters in every different habitat because we know these situations are different. Nick and I are saying, can we blow past all of that and build a 2-parameter model where our 2 parameters are this mystical unstable point and dispersal distance? How far can we go down the road to understand the real observations in nature in terms of those 2 parameters? So here are the data. So this is what we're trying to understand. Here's where we did the releases. So I'm going to show you snapshots every 6 months. These are Kriging plots every 6 months over 2 years. 6 months later, it's spreading. It's outside the release area, but it's not spreading very quickly. A year and a half later, 2 years later, this is an embarrassment. I think you should always air your dirty laundry. I don't know why this is happening. I'm happy here. It's spreading slowly, but it's spreading. Here, it has retreated. The frequency here is slightly lower than we release, and we don't understand that. And we don't understand. Okay. That's release area 1. Release area 2. Release area, it doesn't look so good. It's spreading a little, maybe yes, maybe no. Oh, okay. It's spreading a little. Spreading slowly. A year and a half down the road. Can we summarize this in some way to get a crude approach? So I'm going to show you likelihood estimates of wave speed and all that, but let's just do an eyeball estimate of wave speed first. And you can estimate wave width, and the wave width here is on the order of 400 meters, which corresponds to dispersal distances on the order of 100 meters per generation. You can look at the areas covered by the infection. So you just look at these Kriging plots and ask, how is the area covered by the infection increased? And it increases, albeit really slowly. You can just build trivial geometric models, how the area should increase as a function of wave speed, and you get wave speeds on the order of 12 to 14 meters per generation, assuming 10 generations per year, on the order of 120 to 140 meters per year versus 100 kilometers per year. Okay, so we have reaction diffusion predictions. So this is what we saw. Now I'm not going to go into this, but that third spot, it never really established, and certainly never spread from there. So you just do what comes naturally, a reaction diffusion equation with a cubic dynamic to approximate bistability. So our 2 parameters are the position of the unstable point, and our spatial and our rate of spatial movement. And then you get a classic hyperbolic tangent waveform. So here, redoing everything with likelihood fits. So here are our data measured so we want to make our two-dimensional data into one dimension by measuring distance from the release point, doing smoothing and averaging, and fitting likelihood surfaces. This is the change of the wave front through time. It does increase more or less linearly. And this gets a slightly different estimate. Nick estimates, and this is Barton's work, Nick estimates the wave speed on the order of 17. We're still talking about 170 meters per year. Okay? So, how does that fit in with the reaction diffusion equations? And do you believe the reaction diffusion equations? The reaction diffusion equations are derived from discrete time, discrete space approximations, where you assume that the local dynamics are slow, and you do an approximation of dispersal where you drop off the higher order terms consistent with a Gaussian. Okay, so you're going to do an expansion. Well, do you believe that approximation? So rather than just do PDE, we did discrete time calculations also to compare to the PDE predictions, to look specifically at the consequences of long tails of dispersal, because we know that Aedes aegypti, like every other animal and plant, has a non-Gaussian dispersal kernel with demonstrably long tails. What difference do long tails make? Okay, so first of all, here's the wave width prediction. Cytoplasmic incompatibility is complete. Cytoplasmic incompatibility is the engine that runs this system. Okay, we know the reaction diffusion equation should be a good approximation if dynamics are slow. What makes dynamics slow? In this system, the Wolbachia system, dynamics are slow if you tune down cytoplasmic incompatibility. So I'm going to compare the real value of cytoplasmic incompatibility 1 to weak cytoplasmic incompatibility 0.1 and see how good the reaction diffusion approximation is with weak CI versus strong CI, and ask about the robustness of this wave width prediction. Okay. We empirically observe a wave width about 400 meters, implying sigma is about 100 meters. Okay. Well, here, so I said 0.1, I should have said 0.2. This is what we believe is really going on. This is weaker cytoplasmic incompatibility. Sorry, you can't read this. Observed in the simulations versus predicted from the reaction diffusion. The answer is, if you have relatively slow dynamics, the reaction diffusion is really dead on for the wave width. Even if you make realistic dynamic speed, so CI equal 1, the biggest departures you see for realistic levels of the unstable point are about 10%. Good enough for, I mean, we are not physicists here. I mean, if you're within 10%, you go home quite proud of yourself. So we can use the reaction diffusion prediction to estimate wave speed even with long tail dispersal, is the conclusion I draw from that numerical result. Here's this famous prediction for wave speed. The wave speed is equal to the dispersal distance, square root of the intensity of cytoplasmic incompatibility, 1/2 minus p hat. This is what says, if the unstable point goes above p hat, the wave moves in the negative direction. The variant disappears. So what's significant about this is if this bistable dynamic is true, the wave speed is bounded above by sigma divided by 2. Sigma on the order of 100 meters per generation. So the upper bound is 50 meters per generation. It's never going to go more than 1/2 kilometer per year. Okay? So it's definitely going to go slow. Sadly, that's on the order of 0.25 or higher. So it's on the order. The upper bound, I think realistically, is more like 25 meters per generation. Well, how robust is that prediction to long tail dispersal? And so if you make the unstable point about 0.3. You predict about 20 meters per generation, or about 200 meters per year, and we see 120 to 170. You know, I haven't embarrassed a family, right? I can still keep my job. This is not bad for a prediction about nature. How robust is that prediction? The answer is, if dynamics were slow, it would be basically dead on. I would have to live with that prediction, because even the discrete time, discrete state space approximation say independent of the dispersal kernel, that is the wave speed. On the other hand, if you deal with faster dynamics and you have long tail dispersal, you can really knock back the wave speed on the order of 20 or 30% quite easily. So I say that the reaction diffusion prediction is an overestimate, and I say that what we see in nature is really not badly approximated by very simple mathematical analyses. Okay? So, successfully predicted spread, but it's slow. And people got excited because Wolbachia would spread quickly. So, what, if anything, will the role of spatial spread be in trying to protect a city like Rio? Okay. And the answer is, even these slow rates of spatial spread will produce area-wide control on the order of 2 to 3 years if you're willing to transform on the order of 20 or 30% of the city. You still get to not release in 70%, but if you want to get Rio covered in 3 years, you're going to have to release on the order of 20 or 30%. How late am I? Yeah, so, okay. Yeah, there are predictions about, yeah, let me just show you one of these, because this is nice. How large so you're not going to transform a whole city at once. How large an area of space do you have to transform to create an expanding bubble? Okay? This is a prediction of the radius of the circle you have to transform as a function of the unstable point. As the unstable point moves towards a half, that blows up to infinity, but it blows up in a nice way. It blows up very slowly, and it doesn't really start going up till you get to about 0.4. We think they're around here. This is reaction diffusion. Sorry. And this is the radius of the area measured in dispersal distances. Okay? If the dispersal distance is about 100 meters, this says if you transform a circle with radius about 300 meters, so this is about a half a square kilometer. A square kilometer is more than enough according to the mathematics and according to our experiments. We release in a half a square kilometer and a square kilometer, and we're seeing spatial spread. So these crude predictions are validated, but these crude predictions based on reaction diffusion were conservative. If you look at the discrete time, discrete state space, and you look at long tail dispersal, you can get away with smaller releases, it turns out. Okay, I'm not going to go through this. I haven't embarrassed a family. How about spatial spread? Yeah, my analyses of the releases suggest that we're in the ballpark. Yeah, I have a bunch of results. About the time scale. This is based on simple, trivial geometric calculations based on an expanding circle. Expanding circles at the rate we observe. How long will it take to get 80% coverage if you start with areas that are either 1 square kilometer or half a square kilometer? And the answer is, to cover in 40 generations, 4 years, you'd have to transform at worst 20 or 30% of the city. And this depends on what the unstable point is. You could ask about, I have a bunch of math that Nick and I have done recently. So we have predictions about optimal design of releases. So it's supposed to release spatially in a checkerboard. You're supposed to release in an area and leave gaps of a particular size. How robust are those predictions? We don't know exactly what sigma is going to be. And this is a prediction that I won't go through that says that these are quite robust, that it doesn't matter what the initial frequency is in the release area. Basically, anywhere above 0.6, and you're going to get to the same place in roughly the same amount of time. How about the sizes of the release areas? Well, the size of the release areas in terms of times to coverage, you don't want to underestimate because that's going to blow up. But if you overestimate the release area, the minimum release area, by a factor of 2, you only pay a penalty of about 30%. Okay? So there's a bunch of things that says, okay, we have slow spatial spread, but it's slow but reliable spatial spread, blah, blah, blah. The problem is wave stopping. The problem is wave stopping. So we have this thing that's spreading very, very slowly, okay? But unlike the blob, this thing gets stopped by roads. So I already told you, there's this highway. It's 100 meters across, and the mosquitoes don't make it. The Wolbachia doesn't get from one side to another. So whenever there are significant barriers to dispersal, you're going to have to do another release, okay? You have to do another release because this is a relatively pathetic Wolbachia in the sense that the unstable point is all the way up to about 0.3. If you knock that unstable point back to about 0.1, it would be much harder to stop. Yeah, okay. I had it here somewhere. Yeah, sorry. So if the unstable point is 0.25, a 2-fold increase in population density. So these waves, like all waves, want to go downhill. What does downhill mean? They want to go from areas of high population density to low population density. What gradient of population density will stop them? Well, less and less of a gradient. If the unstable point is 0.25, a 2-fold increase in population density will stop it. If you get it down to 0.1, it takes 5-fold, okay? So let me end with some gossip. The gossip is, and Crystal, maybe you have better gossip, but my gossip is in the areas that we've transformed. So now we've transformed a few square kilometers. We've transformed the area of the city of Cairns that's traditionally had the highest dengue incidence every year. In those areas that we've transformed, we've as yet had no secondary dengue transmission. You still have primary cases come in, but no confirmed secondary cases. So we think we have a viable strategy. This viable strategy is not going to transform cities like Rio overnight. It'll take a few years. I think O'Neill, don't tell him I said this, has been in far too much of a rush to release the first Wolbachia that looks okay. We should be looking at many more Wolbachia to find one that has a lower unstable point. But still, it's incredibly cool that someone who's doing basic biology could make a discovery that may have practical value. Thank you.
So the speakers are now entertaining questions, if any.
Hello, Bernard. Oh, this doesn't work. Does it work? This is better. Better? Yes. So the study in Thailand, I thought was the one where you grouped the behavior, I thought was very interesting because there have been all sorts of criticisms to the climate driving of dengue. And I think it's this confusion about perhaps the different regions or where you look, no? But it was interesting that you went from patterns that had some more seasonal signal and some that had more interannual signal. And you said that you can find some grouping of the behavior of rainfall and things of that sort. But I was wondering whether that gradient has to do with the degree of endemicity. So how epidemic is dengue for perhaps other reasons than the spectrum of the climate, but just the overall level of rainfall or temperature or population densities or whatever. because we would expect that the interannual behavior would perhaps be stronger in the more epidemic places, and that the seasonal signal may be stronger in the more endemic ones.
I'm not sure, but I think that in Thailand, all provinces are very endemics.
Yes, but in a relative, like which ones have, you know, truly lower troughs, and because I think that the sensitivity to climate will vary in that to the interannual, and it would be very interesting to see if you have something that is more more endemic in some sense, and why is that, and perhaps that explains the different sensitivities.
I don't have the answer, but I can
Yeah, it could
check.
be interesting. And the final question was, you said you have UPCA dynamics, which is an interesting mathematical feature of the models, but you said you have it in the data just because you saw the variable.
No, we show that we have
So you showed that
UPCA dynamics
in the data.
in the models.
In the models, okay, in the
In
models.
the data are very short to compute
Yes,
the
that
Lyapunov
was
exponent.
okay,
so-
because I thought you had said okay. So that I can see, and that
But,
the models you are fitting are stochastic anyhow.
Yeah.
So it's very hard to know whether you needed to explain the behavior of the data.
So we do the same on flu, and the parameters are not in the chaotic region. When we fit the parameter with MIF at the time, the parameters are not in the chaotic region, but just at the border.
Okay, thank you. Can I ask one more question? Because you said you should look for a Wolbachia with a lower.
Yes.
Your parameter is that the value of that
Yes. Yeah.
which is an interesting parameter because it's a very practical one. But if you had to, since it doesn't depend on biological parameters that are easily imagined, let's say, more mechanistically, if you had to recommend, how would you look for a Wolbachia that has that property? Do you have a sense?
We don't have an a priori way to evaluate the Wolbachia, where you just put them in and do and you just evaluate them in the laboratory. So the WML pop, the life shortening one, we knew instantly from the first experiment that there were real problems. Okay, so it's just a matter of developing, getting 20 in. I mean, if you're spending $50 million, you could do some experiments, huh?
I was wondering whether it gives you any intuition, whether you have any intuition of what is it about the biology that determines that equilibrium, that unstable equilibrium values. So that
We do.
If you're an entomologist.
So Mercedes, this is what I'm doing. So I'm funded now to look at Wolbachia in 20 different systems in nature. So we're, if you like, bioprospecting and looking at the features. We don't know enough. It's shocking how few of these systems have been studied in nature and how little we know. So different individual Wolbachia haplotypes have different tissue tropism. We know that some of these phenotypes are related to the titer, how much Wolbachia they have. And we know both the protection and the costs are related to titer, but it's not a perfect correlation. So that's specifically looking for variance from that trade-off, because we know high titer variance at best at blocking dissemination, but in the few cases we looked at are generally associated with higher cost. I just say, let's put 20 in and do the cages before we release everywhere.
So for Bernard, so you are in a position of projecting into the future everything that you showed us. Okay, so you can tell us what's going to happen 20 years from now in terms of dengue, cholera, and lots of other diseases. Have you tried to do that? And
Of course not.
but I mean, you could do this. Okay, so for Michael, I'm making an analogy of your system with transposable elements. Okay, So in transposable elements, you have this idea of an inactive element. Is an element that is there that could replicate, but needs the help of another element that is capable of expressing the transposase. Okay, so your two Wolbachia system might be something similar to that. So you have one Wolbachia that cannot do the that express the cytoplasmatic incompatibility, but there is another one that can. And what if one helps the other one? Okay.
That's a great question, and that's so. I said that we've investigated only two. That's a bit of a lie. Scott O'Neill has also tried a combination of two Wolbachia for exactly that reason. And the problem is when he put two in, they were not stably transmitted. So, but that's a very interesting conjecture that you could combine Wolbachia with different properties. So in nature, I said half of all insects are infected with Wolbachia. There are some individual insects, like these Triffidids, fruit flies, some of which have, every individual has 7 different Wolbachia. And we don't know, it's like a little community of Wolbachia within these flies. And we don't know how they interact. So there could be very interesting and perhaps useful interactions.
Questions? So if there are no further questions. He was very, very...
You refuse it?
He whispered, say, no, I haven't tried that. Okay. So since there are no further questions, I would like to thank everyone for your participation. And most of all, I would like to thank the organizing committee for the wonderful atmosphere that they provided us for this very interesting and enticing meeting. Thank you very much.
Thank you very much, Claudio. Thank you very much, Bernard and Michael. So talking about forecasting the future, yeah, there's an open question here. What shall we do with this first conference? Really, we are totally open. It can be the last one. It can be the first of a long series here, in other places, every year, every 2 years. Really, we are totally open to criticism, suggestions, and how to say it, proposals to do it somewhere else and itinerant or coming back here sometime. Well, really, so we won't send you a poll asking for to answer in this authoritarian way. We will just wait for signs of interest or not, and so on. So really feel free to make any proposal, and we'll see whether this can survive, be transformed or not, and so on. Okay, so I'd like also to thank all of you, to thank the speakers who were extremely patient and open to make a work which would be interesting. Really, it was extremely nice to work with you. All of you were extremely open to our humble proposals to make material better available to the audience. Thank you very much to the chairpersons. Thank you very much to the authors who contributed, to the FGV staff here and who helped here too. Thank you very much also to the people from the organizing committee. In all categories, a lot of efforts who were beautiful and which will remain anonymous were done, and this was really great. So maybe to next time. Thank you very much. She's not here. Yeah.